We've been using implicit differentiation, and well, implicit differentiation itself doesn't have a huge number of specific applications. What we're going to use, what we're going to learn today, which is related to implicit differentiation, is very important and very useful. It's called related rates. Basically, what we're going to be doing is we are going to be finding the rates of change over time. And everything that we use, we will be finding a derivative with respect to time, meaning that that everything that we're going to do is going to be over a dt. For example number 1, we have water that's being drained out of a conical tank, meaning that the tank is in the shape of a cone, and they want you to use implicit differentiation with respect to time. So I'm going to draw a picture so you can kind of visualize this. We're going to start off, we have a tank, and we're going to have some water in the tank. I'm going to make it blue. So this water in the tank is going to have a height, which we'll call h, and it also has a radius, which we're going to call r. Now, it starts off and we have a radius and a height, but actually as our water continues draining, for example, when we're down here, the height is actually going to change. So we're going to have a smaller height and a smaller radius as it keeps going along, and the radius is going to change. In addition to that, the volume of the water is going to change. So all three variables are going to change over time. We're going to use differentiation, taking the derivative, to figure out how they change over time. So the first question I asked you was to find dv dt, and I also asked what does it mean in the context of the problem. So to find dv dt, we have, first of all, we have v equals pi over 3 times r squared h. Keep in mind the pi over 3 is a constant, but both r and h are variables. So just make sure that you know what stuff is constant and which stuff is a variable. So for dv dt, that's what we're looking for. We need to use what we know about taking derivatives. I'm going to keep my constant out front and just kind of ignore it. And then I'm going to actually use the product rule. So my first term is r squared. My second term is h. So when I use the product rule, I'm going to do my first term, r squared, times the derivative of my second, which is going to be dh. We're taking the derivative over time, so it's going to be a dh dt. Because my h is not a t, it's going to have to be, I'm going to have to use implicit differentiation and keep it written as dh dt. If I had a t variable, then I would just take the derivative normally. The next thing I'm going to do is, I'm going to do then plus the second term, which is my h, times the derivative of my first term. So derivative of the first term is 2r, but because we're differentiating with respect to t, I have to multiply that by a dr dt. And this right here is actually my answer. There's a little bit of stuff that you can do to simplify it, but you don't really need to do anything more than what we have here. So the next thing I asked you is, what does dv dt mean in the context of the problem? In addition to asking you what that means, I'm actually going to also talk about what the dh dt and the dr dt mean. So dv dt means the rate of change of the volume with respect to time. I'm going to write it as WRT, that means with respect to, just so that I can abbreviate it a little bit. And you might be able to guess the dh dt is the rate of change of the height, and the dr dt is the rate of change of the radius. And like I said earlier, all of those things are changing as the water is draining out. So those are all going to be part of our equation. If anything you had was not changing, and there will be cases where things are not changing, then you can actually write the drdt or the dHdt or whatever variable as 0, and that makes your problem a little easier. So we're going to do an example. This one I think is actually a really nice one to start with because it's not a word problem. I am going to tell you right now that most of the problems you get will be word problems though, so they're going to be a little bit harder. So this one says, given the function y equals x squared plus 3 and dx dt equals 2 when x equals 1, we want to find dy dt when x equals 1. So the way that we're going to do this is by taking the derivative of everything with respect to t, and if it makes you feel better about doing this, you're welcome to write this as d dt of this entire thing. Our first thing is going to be derivative of y with respect to t, which we just write as dy dt. The derivative of x squared with respect to t is going to be 2x times dx dt. Thankfully, the derivative of 3 is just 0, so that makes the problem a little easier. Now all you're going to have to do is substitute in, we don't know dy, that's what we're trying to find. We substitute in for 2, we substitute in 1 for x, and we substitute in 2 for dx dt, so my answer is 4. I am going to tell you that you will occasionally have something like a y in here. If you had a y in there, you would have to go back to the original equation and plug 1 in for x. We don't actually have that in this case, so we're not going to worry about that, but that might happen later on. Let's do another example. So a pebble is dropped into a calm pond, causing ripples to form in the form of concentric circles. Remember, concentric means they have the same center. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. Then they ask you when the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So I gave you here a list of 4 steps, and these work pretty well on these problems. It's good to go, just slowly go step by step. The first step is always going to be to identify the quantities that you know, figure out what you need to find, and also if you can make a sketch and label it, I think that's also a really good idea. So we have we have a series of circles, and what's going to happen is the circles are actually moving outward. And as they move outward, they're going to just get bigger and bigger and bigger. So as the circles get bigger and bigger, I want you to note and think about the fact that both the area of the circle is going to increase and also the radius is going to increase. So we're actually looking for the rate that the area is changing at when r equals 4. So let's go ahead and actually write out the variables that we know and the ones that we don't right now. First thing they tell us is the radius r is increasing at a constant rate of 1 foot per second. So that rate of change of the area is not going to be r. Don't write r equals 1 for this. Be really careful. That is going to be our dr dt. This is the rate of change over time. That is 1 foot per second. You can kind of tell when something's going to be over dt because the unit is over a time. So the unit's over seconds. The radius is in feet. The time is in seconds. So the dr dt, the change in the radius over time, is in feet per second. The other thing they say is when the radius is 4 feet, so that is our r. At what rate is the total area of the disturbed water changing? So we are not looking for the area at a specific time. So you might think, oh, we're looking for A? No, we're not. We're actually looking for dA dt because we're looking for the rate of change of the area. So now we have a few things. We have R, we have A. We're going to start by writing an equation. Do not worry about the fact that we have a dr dt and a dA dt. We're going to try to find a way to relate area and radius. And the area of a circle is pi r squared. Hopefully you remember that one. That's one that you've probably seen many times. Now we're going to get our dA dt. So that one we use the chain rule to implicitly differentiate. This one's pretty nice because there's not any there's no products, there's nothing really hard in this one. So I'm going to take the derivative of that entire equation, a equals pi r squared. A is a variable, r is a variable, pi is a constant. When I take the derivative, I get dA dt. By the way, that's nice that we got dA dt because if I had anything other than a on that left side, I would need another variable in this step right here in that first step. So I get dA dt is equal to pi. Now I'm going to do the derivative of r squared. That's going to be 2r times dr dt. Once I have that, now I'm going to substitute all my values and then I'm going to solve it. So I don't know dA dt, that's what I'm looking for. I have pi times 2r, or 2 pi, times my r, at that point is 4 feet, times my dr dt, which is 1 foot per second. If I multiply that all out, I get 8 pi. And make sure that you get your units. It's going to be in feet squared, which is fine. We want our area to be in square feet per second. And that's my answer for that one. Don't forget those units. That's a really important part of it. Usually you will be asked to write what the units are.